Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. This is Lesson 24, Introduction to Simultaneous Equations. Okay, the first classwork exercise is an exercise. So see if you can do it. Pause the video and come back and we'll see how you did. Okay, so assuming that you've already tried this, it says Derek scored 30 points in a basketball game. So there's the total he got. And not once did he go to the free throw line, which means it's a one-pointer. That means that Derek scored 2-point shots and 3-point shots only. Okay, so he only got 2 and 3-point shots. List as many combinations of 2 and 3-pointers as you can that would total 30 points. So this would be my X and this would be my Y. So if I think about this, if I start with the 3-pointer, if I have 30 points I have to score, and I get a 3-pointer, then that leaves me with 27 more points to get. 27 is odd and 2 won't go into it, so I can't get odd numbers of 3-pointers. So they have to be even. So there's the hint there. Can only have even 3-pointers, even number of 3-pointers. Okay, so I would start off with the Y. So I will put in 0. So if I don't get any 3-pointers, that 30 points divided by 2 is 15 2-pointers. So it's 15 2-pointers and no 3-pointers. Okay, so also if I divide 30 by 2, I get 28 and 3 won't go into 28. If I divide 30 by 4 or by 2 or subtract 2 from 30 and get 28 and subtract 2 again and get 26, 3 won't go into 26. Subtract 2 again and I get down to 24. So there's something going on here. If we take the least common multiple, that is what we're going to need to do for both of these for our amount of change. So I can't get odd numbers of 3-pointers because that would give me an odd number when I subtract 3 from an even. So if I go down to 2 here, 2 3-pointers is 6 points, leaving me with 24 2-pointers, which would be divided by 2, 12 2-pointers. So I increased by 2 and I decreased by 3, and multiplication's repeated addition, so we now have our pattern. So I'm just going to add 2 each time and subtract 3 each time. And there are the possible solutions. So 15 times 2 is 30, plus 0 is 30. 12 times 2 is 24, plus 2 times 3, which is 6, which totals 30. 9 times 2 is 18, 4 times 3 is 12, 18 plus 12 is 30, and so on and so on. No 2-pointers, 10 3-pointers, 10 times 3 is 30. So there are the possible outcomes. Now it says to write an equation that describes this data. Well, we have x's and we have y's. So what we're doing is we're adding how many 2-pointers we get and how many 3-pointers we get, and we want to total 30 points. But I can't just say x plus y equals 30 because 15 plus 0 doesn't equal 30, but this made our statement true. So what I have to do is come up with a coefficient that I'm multiplying the number of shots I get by. So in other words, if I throw a shot and it's worth 2 points, then it's 2 times 1 or 2 points. If I throw 2, it's 2 times 2 or 4. So the coefficient is the value of the shot. So my y is going to be 3. So 2-pointers and 3-pointers. So there's my equation to describe this data. So obviously if I just pick one of these, I didn't check 6 yet. If I plug 6 in here, 2 times 6 is 12. 6 times 3 is 18. 12 plus 18 equals 30. Okay, number 2, it says Derek tells you that the number of 2-point shots that he made is 5 more than the number of 3-point shots. Okay, so the 2-point shots he made, the 2x, is 5 more than. So the word is means equals, and more than means to add, but remember we have to read it backwards. More than the number of 3-point shots, 3y. So 5 more than would be 3y plus 5. So Derek tells you that the number of 2-point shots he made is, okay, so write an equation to describe that data. We've done this over and over in class, so I am going to just come up with the equation just from the sentence. And it says 2-pointers. The number of 2-point shots is 5 more than the 3-point shots. Okay. So whenever I'm doing a problem like this, you have to obviously check this. So I'm just going to leave this here for now. I'm just building off of what we used last time. It may work, it may not. We'll have to take a look. And so now we want to, how many combinations can you come up with this scenario? Don't worry about the total number of points. Okay, so if I throw 0 2-point shots, 5 more than the number of 3-point shots, well, there's no such thing as 5 more than. So is Derek tells you the number of 2-point shots he made is 5 more than the number of 3-point shots. So I can't start with 0 because 0 is not 5 more than. We can't get negative values. So if I say 5 here, 2-point shots is 5 more than the number of 3-point shots. Well, 5 more than the 3-point shots would be 0. Okay, so if I choose 6, well, 6 is 5 more than 1, and 7 is 5 more than 2, and 8 is 5 more than 3, and 9 is 5 more than 4, and 10 is 5 more than 5. So there's a list of numbers that we could use. Now, if I plug any one of these in, if I plug 6 in here, 2 times 6 equals 3 times 1 plus 5. 12 equals 3 plus 5. Well, that is not true, so I don't like my equation that we just came up with. So what's happening here? We do not need the coefficients. So if we just have x equals y plus 5, then we get the proper equation that will come up with the answer, because the key here was don't worry about the total number of points. So number 3 says, which pair of numbers from your table in exercise 2 would show Derek's actual score of 30? So 10 times 2 is 20, 5 times 3 is 15, that's 35. 9 times 2 is 18, 4 times 3 is 12, 18 plus 12. So the answer is the points 9 and 4. So that's the answer to number 3. Okay, number 4. Efren and Fernie are on a road trip. Each of them drives a constant speed. There's the key. We have a constant ratio or constant proportion, constant rate problem. Efren is a safe driver and travels 45 miles per hour for the entire trip. Okay, so that is our C. C equals 45 mph. Fernie is not such a safe driver. He drives 70 miles per hour throughout the trip. Okay, so Fernie drives 70 miles per hour throughout the trip. So Fernie's constant is 75 miles per hour. Or 70, not 75. Fernie and Efren left from the same location, but Efren left at 8 a.m. and Fernie left at 11 a.m. Assuming that they take the same route, will Fernie catch up to Efren? If so, approximate when. Okay, so now we need to keep in mind that C equals distance divided by time. So we're talking about Efren here. So Efren left at 8 a.m. Let me keep the right colors here. Efren left at 8 a.m. and Fernie left at 11. So Efren left 3 hours earlier. And assume that they take the same route. Will Fernie ever catch up? If so, approximate when. So Efren is going to drive for 3 hours longer to determine if they catch up. To catch up, you'd have to reach the destination at the same time. So Fernie's got to go fast enough to catch up to Fernie within those 3 hours. So that's what we're trying to determine. So if C equals D over T, which we would convert to X over, or Y over X, Y divided by X, then we would say 45 miles per 1 hour equals Y over X. So this is very similar to a prior lesson. I think it was 12, I think. And then when we cross multiply, we get 1y, or y equals 45 times x. So y equals 45x, but don't forget this extra 3 hours. So it's going to be number of hours plus that 3 hours, because in 3 hours I can drive how far? 45 times 3, so I have to multiply this and distribute. So my equation is going to be y equals 45x plus 45 times 3, which is 135 miles in those 3 hours. So x number of hours times 45 plus those 135 miles at 45 miles per hour for 3 hours. So there's my equation. Y equals 45x plus 135 miles. Now B says to write an equation that represents Fernie's constant speed. Well, Fernie is driving at a rate of 70 miles per 1 hour, so that equals our y over x, and when we cross multiply we get 1y, or simply y, equals 70x. There's no additional hours for this, so that is Fernie's equation. Okay, so now we have a scenario that's called a system of linear equations. Simultaneous equations here, they're calling them. They're considered a system when we graph each one on the same coordinate plane. Okay, so one is y equals 45x plus 135, and y equals 70x is the other equation. So part C says to write a system of linear equations that represents this situation. So a system of equations is those two equations. So I'm going to say y equals 45x plus 135, and y equals 70x. So there's my system of equations. System just meaning more than one equation graphed on the same coordinate plane. So now D says to sketch the graph of these. Okay, so I will do Fernie's in green, and who was the other person? Can't remember their names. Efren and Fernie. So I'll do Efren in green and Fernie in blue. Okay. So if I graph these, remember our B is our y-intercept. So at 135 is somewhere between 100 and 150, and I don't want to estimate. So I'm going to plug values into this. So if y is 0, I get 135. So I need to find values that would come out to be integers. And is there a way to do that? Probably not. So 45 plus 135, 45x plus 135, here's 100, and 150 is here, so that's a distance of 50. So 35 is a little bit more than half of 50, so I would say maybe right about here. So I'm just going to do this. And then if I go 1, well, 45 plus 135 is 180. So at 1 hour, or at an additional hour of driving, it's going to be 180 miles an hour, 150, 60, 70, 80, 90. So 80 is about right here. Okay, so now I'm just going to use those 2 points. Actually, let me do another one just to be a little more accurate. So 45 times 2 is 90. 90 plus 135 is 225. And that is halfway between 200 and 250. So at least that's a half one. Okay. All right, so now I'm going to draw a graph of that. So I get a ruler, and I'm going to put the ruler at my first point that I drew or plotted and go through the third one. So my equation, I really don't care what's going on less than 0, because we can't go negative distance or time. Negative time, I mean, or negative distance. So there's the equation of how far the first guy's driving at 45 miles an hour. Okay, so now we have the other scenario where he's driving 70 miles an hour, but he doesn't have any additional hours he's going to drive because he's doing catch-up. So at 11 o'clock, he's starting right here. Well, at 11 o'clock, where is the other driver? That's 3 hours later. The other driver's right here. That's how far he's gone. So this guy has to catch up to him, and he's going almost twice as fast. So if I choose 70x, 1 times 70 is 70, so that's about here. 2 times 70 is 140, which is about here. And 3 times 70 is 210, which is roughly here. And 4 times 70 is 280, so that's about here. And 5 times 70 is 350. Okay, so we're catching up. He's going to catch up to him eventually. And as you can see, this line's steeper. So if I keep doing that, let's just keep going, because the 70, multiplying by 70 is easy. 70 times 6 is 420. So now I'm at 420, which is somewhere around here. Okay, so I paused there for a moment because I'm thinking that this would not take that long, and because you have to take into consideration understanding what the problem's doing. And I thought he would have caught up to him quicker. He's almost going twice as fast, so it shouldn't really take almost 6 hours to catch up. So I checked my values on the blue, and those are correct, but the green, I think, is off a little. So let me do this. Let me get rid of that line, and let me choose another point. Let me choose 6 in my y equation. So if I choose 6 for this, then it'd be y equals 45 times 6 plus 135. And y equals 6 times 5 is 30, 6 times 4 is 20, 270 plus 135. So y equals 5, 1, 2, 3, 405. So after 6, he's going 405. So it's just a little over 400. So actually, no, that's correct. So I'm going to put my line back. No, that's about right. Okay. So now I'm going to draw a line for the blue. So I put my ruler on the first point, rotate it so it's as close as possible to my points I plotted, and draw a line. Okay. And this continues on. So there's the graph. And so he would catch up at the point where they intersect. Okay, so these two equations would intersect at between 5 and 6 hours. So that's what I would say. Sketch the graph, I did that. And now it says, will Fernie ever catch up to Efren? If so, approximately when? And I'd say yes, comma, between 5 and 6 hours. Between 5 and 6 hours of driving. Between 5 and 6 hours. H-O-U-R-S. Okay. Yes, between 5 and 6 hours. At approximately what point do the graphs of the line intersect? And it's around close to 400 miles. Okay, my graphs might be off just a little bit. It could have happened down here further than right there. It could be down here more. So I'd say close to 400 miles, and that's close enough for what we're doing right now. So it says what point. So now I put these two together. So I would say, I don't know, 5.5. So the point would be 5.5 or 5 1/2, comma, and I'd say around 400. So that's an approximation by doing it with the graph. Okay, here's number 5. Jessica and Carl run at a constant speed. Okay, so we have this scenario. It's constant. Jessica can run 3 miles in 24 minutes. So her C equals distance over time. So her speed is 3/24. Her constant rate is 3 miles in 24 minutes. Carl can run 2 miles in 14 minutes. So Carl's constant is 2 miles in 14 minutes. They decide to race each other as soon as the race begins. Carl trips and takes 2 minutes to recover. Okay, so that's a scenario where he's starting 2 minutes later. So she's got a 2-minute head start. Okay, so there's our scenario. Write a linear equation that represents Jessica's constant speed. Make sure to include your equation to the extra time that Jessica was able to run, which is 2 minutes. So C equals 3 over 24. 8 times 3 is 24, so this reduces to 1/8. So now that we realize that y equals cx, we don't have to go through all that cross multiplication. I can simply say that her equation is y equals 1/8 x. But don't forget, she also had a 2-minute head start. And that includes the rate she's going. So it's going to be 1/8 times the quantity x plus 2. So therefore y equals 1/8 x plus 1/8 times 2 is 1/4. So her equation is y equals 1/8 x plus 1/4. His equation is going to be y equals 2/14 is 1/7. So his equation is going to be 1 over 7x. So there are our two equations. So it says write a linear equation that represents Carl's. Okay, I just did that up here, so it's supposed to be here. And this is his constant rate, so I'll move that down as well. And so there's our equation for Carl. Now it says to write a system of these two equations. So a system is y equals 1/8 x plus 1/4. And this one is y equals 1 over 7x. Now it says to sketch a graph of these. So I will keep these color-coded. So going up 1/4 is 0.25. So 0.25 is approximately here, because 0.3 would be here. And then I'm going up 1 over 8. So if I go up 1 whole unit, that's 0.25 to 1.25, and then over to 8. So be careful with your unit measurement. So this is my second point right here. Up 1 over 8. Get a ruler. And graph as accurately as possible. Okay, so there is her constant rate equation graphed. Okay, now we're going to sketch, I think his name was Carl. Yes, Jessica and Carl. So Carl, keep in mind that Carl is going to start at 0. She got a she got a head start there. Okay, so Carl starting at 0, and 1/7 means to go up 1 and over 7, which is right here, the point 1 comma 7. So if I graph those 2 points, remember to be accurate with this, then we can determine where they're going to meet, where he is going to catch up with her. Okay, so it looks like it happened right about here. That's where they intersected. Okay, so that value is after the time 15 minutes, or is it hours? 15 minutes. After 15 minutes, and they had gone 2.1 something miles. So it says use the graph to answer the question below. If Jessica and Carl race for 3 minutes, who would win? So I go back. 3 minutes on the graph is right here. So the person who would win is the person who has a higher number of distance. So it is going to be Jessica. Jessica would win because it says race for 3 miles. Use the graph to answer the question below. If Jessica and Carl race for 3 miles, who would win? Okay, I need to be careful there. So we're talking about distance, not time. Okay, so we're doing miles, which is our numerator, the top. So this is my y, miles. So 3 miles 3 miles is off the grid, and it would actually be Carl because he caught up to her at 15 miles or 15 minutes, which was just under 2.2 miles, between 2 and 2.2 miles. So once he took the lead, there's no turning back. He's running faster than her, and she can't catch up to him. So if the race went for 3 miles, then Carl would have won. So in 3 miles, he is ahead of her. And running at a faster pace. Okay, I decided to fix that so you could read it. Carl would win because he passed her around 2.1 miles and is running faster than Jessica, so she would never catch up. Part 2 says at approximately what point would Jessica and Carl be tied? So if we go back, that means where did the lines intersect? So it was at the time 15 minutes or 2.1 miles roughly. So it says at approximately what point? So when you see that word point, they don't mean time, they don't mean distance, they mean both time and distance. So it means a point. So it's at 15 and approximately 2.1 miles. That's where they would be tied. Okay, so it says explain. I'm not going to write anything here, but if you look on the graph, that is where the two lines intersect. He is going faster and catching up, and it is at the point 15 minutes and approximately 2.1 miles that they caught up to each, or he caught up to her. Okay, that is the end of lesson 24. Review this lesson summary and go to your problem set.